Okay, can everybody hear me?
Yes.
Okay, good.
Yes.
Good. I gave you some things to look at, and hopefully you did, on on solving circuits with phasors and going through complex numbers. Now, there's a lot that I can get into, but I figure I'm going to show you the essence of it today and how to use it and really how to solve these things. You're going to see a lot of these circuits problems boil down to something that's very easy to do. And if I can get this.
Dr. Vagansky, you said to remind you to make me a co-host so I can record it.
You are absolutely right. You're a co-host. If anybody else wants to record it, she's going to upload it to YouTube for the whole class. And the reason I'm doing that is even though this show's recording, I'm not convinced we won't have additional problems just simply because the sheer numbers of people that are using Zoom to record their lectures. And can you put this on GroupMe, by the way, Jessica?
Yes, sir.
So she'll put a link to the actual the video, today's video, as well as hopefully you'll have one on Zoom. They should be on Zoom, but I know that I've had some problems, at least with 2 lectures. And what I'm doing now is getting the camera up. I'm going to share the screen in 1 second if it comes up okay.
I'm wondering, since you're already recording it, I don't think I have to do anything. While I'm looking at it, it's showing that it's recording.
Yeah, but are you know, when you get this, you're going to be asked if you want to upload it to the, I think the Zoom, or do you want to upload it to to YouTube? Put it on YouTube, please. Okay.
I will.
Come on, camera. All right, one last time. I don't know if anybody else had a problem. There's been a ton of updates in the last, say, 5 days. On my, I use Windows 10 and it's through the university, but some of these updates I think are causing problems with some of the devices. Anyway, first, does anybody have any problems at all or any questions about the videos I gave you? The woman at Georgia Tech did a really good job saying she wasn't going to go into the essence. Does everybody see the screen right here, by the way, that I'm sharing?
No, sir.
Thank you. Appreciate that. Okay, do you see a yellow tablet right now?
Yes, sir.
All right, I was starting by asking if first, if you looked at the videos by the person at Georgia Tech, they did a great, in my opinion, they did a very good job showing you the simplicity of some of this stuff. Now it's just to prime you. I'm going to go through today, first talk about complex numbers, then talk about an application of how you solve circuits using what's called phasor analysis, but first complex numbers. Now, most of you, matter of fact, I think it's a prereq that you've been exposed to complex numbers before you take this course. So hold on for 1 second. I'm trying to forget it. I was trying to be able to see you, but I can't right there. I'm going to have to just deal with what I've got. So for complex numbers, most of you have had this. Give me 1 second. If you, somebody's got a comment question. Yes, the last Zoom lecture was recorded, I believe. You go to Canvas, you should be able to get. For complex numbers, All right, first, what are they? Well, generally, I like to do this in terms of a graphical sort of presentation. A complex number has a real and imaginary part. So if I say A is a complex number, this tilde just means it's complex and it has no other significance. Suppose it was equal to A plus JB. The A is a real number. J indicates whatever its coefficient is imaginary. Now what this looks like in the complex point, can everybody hear me okay, by the way? I'm really trying to,
Yes.
okay, I'm trying to broaden this, but I don't know if I'm going to be able to. I'm trying to see everybody. There we go. I don't know why it wasn't working. Okay, now I can see everybody and nobody has their camera on, so it doesn't matter. Anyway, at least I can see thumbs up. This is a real and imaginary part. Graphically, what this looks like is this. So please try to follow me on this. This is going to be the real axis, and it's just a graphical illustration of this. And this is called the imaginary axis, or what they usually do is put a J down here. The reason we don't use I for imaginary is because we use I solely for current. We save that letter for current. Now what this looks like is simply, if this is the real axis, well, you come out until you go to the value A. Can everybody see this okay? You're just going out A, and I'm going to do a concrete example. It's JB. Well, this is J. This would be positive J. This would be minus J. So wherever B is, it doesn't matter. It's up here. Now, if you see where these 2 points meet, assume you have crosshatch, this would be the point A comma B, where A would be the real, J would be the imaginary point. And that is A, as I showed it, tilde. Does everybody follow me on that? It's just like a graph, an XY coordinate system, okay? Y'all see me on it? See this? It's straightforward. There's nothing tricky. Normally, the way they illustrate complex numbers is not just with this, a real and imaginary. They'll also say it's a magnitude, and this would have the magnitude of A tilde here. Y'all follow me? It's going to be a magnitude from the center point here, the origin, to the point of observation where the actual coordinates are, the real and imaginary point, and it's at an angle. So they'll put a symbol here that indicates angle, and this would be the angle. Now I'm going to make some comments about that in a second. All right, that's one way. You've seen this before. That's a magnitude and an angle. Another way that is identical to this, but is useful mathematically for some things, is called the exponential form. Does anybody know what the form I just showed you there is called? Anyone at all?
It's a little out of focus.
Oh, thank you. All right, what is this form called? Let me back up. Does anybody remember what that form's called from the days when you had mathematics, formal math courses? That's called the rectangular form. It has a real and imaginary part. It's like plotting an XY grid point, right? All right, this is called the polar form. You don't need to know these things. This is rectangular. That's polar. There's one other form, and I'm going to show you this. So I can say A phasor here can be A plus JB. That's the rectangular form. Or it can be magnitude of A at a phase angle theta. And theta can be in either degrees or radians. There's no requirement on what that is. Or it can be, and this is the exponential form, it can be magnitude of A, and it's had this form and this form have the identical amount of information, but we put this to e to the j theta. The angle is in the exponential. Y'all follow me? All right, this is rectangular, this is polar, and this is exponential. How many remember seeing at least some version of this somewhere? And now everybody here should have seen this in your mathematics courses because it's a prereq for this class. However, I have taught this course enough times to know some people don't recall it, even though they were supposed to have been exposed to it. And it doesn't matter if you have or haven't. You're going to find out that this is very easy because we're dealing with engineers that live in a system where you talk about magnitude and angle. Now, the way you get the magnitude of A phasor, is simply the square root of A squared plus B squared. I'm making a point of that. And here's why. Because what some people will do is this, and I want you to note this is wrong. They're going to say, well, the magnitude of A plus JB, and this is incorrect, is A plus JB times A plus JB square root. You all follow me what I've done? I've multiplied the two A vectors, right? And then I took the square root. Now, you know why that's wrong? Because what happens there? I get A times A, or A squared, right? And then I have JB times JB. What is J, by the way, from last time?
Square root of -1.
Right, you multiply that. So here, what do you see happening? Well, you're going to have what? You're going to have plus 2JA times B. That would be the inner and then the outer product. And then you would have minus B squared. You all see that? You see that this is unequal to A squared plus B squared square root, right? That's the magnitude. And you can see it right here. It's a right triangle, right? You would go this way and up. So the magnitude here of the line would be the square root of this side, which is A, and this side, which is B squared, A squared plus B squared square root. So you don't do this. You don't take A plus JB times A plus JB and take the square root. This is wrong. I'm just pointing that out. Now, your calculators are wonderful because your calculators will go from real to imaginary numbers seamlessly. How many of you use your calculators to do this? Just raise your hand if you have. James, did you raise your hand just now? No. Has anybody done this? Has anybody used the real? You have, Callan? In what class?
Any class with imaginary numbers, I always try to use my calculator.
Well,
when I can.
I mean, what major are you?
Industrial and systems.
Do you use these complex numbers in industrial and systems courses?
Not in any of my INSY courses, but definitely in like calculus courses.
Okay, that's all I need to know. Everybody should have been exposed to this, so it's nothing new. I'm just trying to make sure we're all on the same page, bringing everybody up to speed, okay? Now, why am I doing that? Well, last time I said that, remember, what I'm showing you are all the same thing, essentially, right? I'm going to cut to the chase on this and quit playing around. I want to give you a concrete example. Suppose I have A is equal to 2 plus J2. That would be in rectangular form, right? If I plotted that, what would it look like? If this is the real and this is the imaginary axis, it would go over 2 this way, up 2, and it would look like this, right? It would just be a straight line here. You all see this? What would the magnitude of that? 2 plus J2.
Square root of 2 squared plus 2 squared.
It's square root of 2 times 2, right? 2 squared plus 2 squared is what? 2 times 2 squared. Square root of that is square root of 2 times 2, right? So the magnitude would be this. What would the angle be? Now you can see this, right? What's that angle?
45 degrees.
Right, 45 degrees or pi over 4 radians. Either one is correct. Correct? Everybody with me? Now, what would that be in terms of the exponential form? I recommend in the exponential form that you get used to writing the angle in radians, and I'll tell you why later, but you can leave it in degrees if you want for now. The magnitude of this would be 2 square root of 2 e to the j, and it would be pi over 4 radians. Now, anytime you see pi over 4, pi over 6, it's implicit it is radians. Do y'all follow me, class? One last thing. What if I had this number? Call it b tilde. And let's say b tilde is equal to 2 minus j2. Right? That's a complex number. Do you all agree?
Yes.
All right. Do it in polar. What's the magnitude of that? Well, you can plot it, right? What's the difference? If that's real and that's imaginary, I'm still out 2 in the real, but now I'm down, right? I want to show you this and make sure you see this. This is an important point. So the actual point I would be at would be what? 2 comma minus 2 if it was real imaginary, right? And that would be it. Do you agree, class? Now pay attention to this. What's the magnitude?
2 square root of 2.
2 square root of 2, right? Same as before. How many, y'all see that? The magnitude is the same, right? It's 2 square root of 2. But what's the angle? Now here's the point I didn't make. Anytime you measure an angle from the real axis in this direction, in the clockwise direction, it's implied negative. Y'all remember that from when you had trig and stuff like this, guys? So it's negative. This would be minus 45 degrees, right? Or I could say B was equal to 2 square root of 2, e to the j, and would be minus pi over 4 radians. Agreed? Now I'm not doing anything here that's trying to dazzle you or just whip through it. I'm assuming you've seen this before and this is triggering memories. Can I just get a response to see how many at least understand what I've done and why I've done it? Now, I'm going to say one other thing that is important. Thank you very much for your responses. It's very, very important to know that J anything is not in the observable real domain. We here, Earthlings, live in a domain of X, Y, and Z spatially in time that goes on. The J domain is not observable. Is everybody clear on that? If you ever have a good physics professor, when he does quantum mechanics, he's going to make that absolutely clear. Has anybody had quantum mechanics? I'm just curious. There's, I think, a few dual majors in here. Anybody at all? Well, I tell you, if you are people that love bizarre things, you love quantum mechanics. I mean, if you get off watching Star Wars or some of these other things, then you're going to love it because it's crazier than any of that stuff. Anyway, it deals with something called the Schrodinger equation. The solution to that is actually something that means nothing, but it can have an imaginary portion to it. It's when you take the solution to the Schrodinger equation and multiplying by its conjugate, you get the probability of something being in space-time at a point. Enough said about quantum mechanics. You'll see that quantum engineering is on the horizon. Everybody's heard of nanotechnology. Well, that implies a lot of stuff that's quantum engineering, which implies using quantum mechanics and the Schrodinger equation. Have you all heard of the Schrodinger equation? You're engineers, you should at least heard that word. Thank God. All right. Yeah, you don't like it? I didn't like it either. I got called I was half asleep in an 8 o'clock class, and I had a German professor who was extremely demanding. And I remember him looking right in the eye, asking me a question that had to do with solutions to partial differential equations and cylindrical coordinates. And I just looked at him and didn't respond. And he said, "What are you, stupid?" And I'll never forget that. And from that on, I always made sure I paid intimate attention to everything that guy said. It's a true story. All right, now, why did I do all that? Should be a logical question. And can everybody hear me? Okay, here's why. Normally, when we have a circuit, all our stuff was in DC before at a constant frequency, right? Y'all with me? In other words, if we had a circuit or a system, that's a circuit. And we had a source that was a battery. If our output was here, the current through this I would be a constant, right? Y'all give me that? It would not be time varying. Agree, class? If you have a battery driving it, the voltage or current, whatever I wanted on a resistor or any resistors would always be what? A constant, not time varying. Y'all follow me on that. This is very important, right? All right, now here's the second part. If I would put into a circuit, and I'm not going to prove this, if I would put in something that had V naught cosine of omega naught t as the voltage source, That little wiggly line means it's going to be a time varying but constant frequency waveform. A cosine of omega t is at a constant frequency of omega naught in radians per second. A sine of omega t is at a constant frequency of omega naught. Okay, are you with me? Well then, if you have this and you put it into any system that is linear time and varying, I didn't put that down, but it assumes linear time and varying. Then if this is the interesting point where we want the output, then both the current and voltage will have some magnitude for current. It'll have a magnitude and it will be at the same exact frequency as this, but it may have a possible phase angle change. And I want to say that all voltages in the circuit here too, if I call this VRL of t, right there, would have some I'll call it VRL here, 0. And it would be times cosine of omega naught t plus some phase angle. Now the question is, the logical question is, well, how do you get I naught and how do you get the value of the phase angle? That's the logical question. I just made the assertion that everything's going to vary at that frequency, but there can be both a magnitude difference, or there will be a magnitude difference for the current, and there's a phase angle. Now I'm going to show you how, okay? Are you ready? So I'm moving it down, and I'm going to make this answer. I've got to make one other statement. You don't need to write this down. You just need to listen to me.
Sorry, can you go back up for 1 second? Thank you.
We're going to be doing a lot of this, so you really don't need to write that carefully. Okay. All right. Now here's going to be my assertion. I said if this was the input, the current and voltage would vary as this, right? Now, if you go ahead and don't write this down, just think about what I'm saying. Please just listen. If I would add plus JV naught here times the sine of omega naught t, then these are two, I'm saying I'm adding that as the input voltage. I'm saying this plus this will be the input voltage. Then the output here would also have plus J I naught times the sine, and I'm running out of room, of sine of omega naught t here, and there would be a plus J VRL of 0 times the sine of omega naught t. I don't want to spend any time on it. Do y'all follow me? If you put a first source in here and you get an output, and then you add to that a second source, the second source will give rise to a functional form of current out here that will just be basically a replica of this, only it'll have sine, it'll have an imaginary J. And don't worry about that. If you want me to prove it, I will, but not here. I'll prove it in the office hour. Now, I'm going to show you how interesting this is. And this is the money. This is really the money. Now, you all remember from last time, this you might want to write down, that V naught e to the j omega naught t was equal to V naught times cosine of omega naught t plus j V naught times the sine of omega naught t. Y'all remember that? That was what law that, or what identity did I use there, class?
It's a little bit out of focus.
I'm trying my best to. Are you with me? What did I do there? When I had e to the j omega naught t, I converted it to a cosine plus j sine. Anybody?
Euler.
Euler's identity, right. It's a godsend. Now, one thing you notice, if I take the real part of V naught e to the j omega naught t, I simply get V naught cosine of omega naught t. Do y'all see that? Are you with me? If this is what this represents, then the real part is just that, right? Because this is the imaginary part. Remember, anything times j is imaginary. Do y'all follow me?
Yes.
All right. Now, here's why I'm doing that. And this is the bottom line. When we solve systems or we solve circuits problems, we don't use a cosine waveform or a sine. What we do is assume the source. Let me talk my way through this. Don't write it down, just follow me. What we do is assume the source voltage is actually going to be V naught times e to the j omega naught t right here. Now, that's not a real thing that can be built because it has a real and imaginary component to it, right? But we do it simply because it'll allow the real solution to manifest. And I know the real voltage is what? Just the real part of V naught e to the j omega naught t, right? That's the actual voltage, V of t. Do you agree with that? All right, now, but if I use this and I put it in a circuit, it can be any circuit at all. Doesn't matter what it looks like. I'm just going to black box it. And I want to know what the voltage or current is through any element. And I'll just put an R here. I will know that the current I of t through any element will have some magnitude I naught. It will vary as e to the j omega naught t with a possible phase angle, if this is the driving function. And the voltage here on the output, or wherever you want to call it, VRL, will be equal to simply VRL naught times e to the j omega t plus a phase angle. Now, I say that, and if I wanted the actual observable, just listen to me, what I would do was take the real part of this current or the real part of this voltage. Now, the best way to do this is for me to show you an example. I really don't want to burn a lot of time here. Once you see this being used, you'll say, why did you spend all that time doing this? But I'm just trying to say to you that anytime you have a linear time invariant circuit, the fundamental frequency that the source voltage varies at, be it DC or anything else, will be the mathematical time varying form that all voltages and currents will vary at, with a magnitude and a phase change. Now, just bear with me on this because I'm getting to the essence of it. So when we have an inductor, last time I think I was doing a capacitor, but I'm going to start with simply an inductor. An inductor symbol is L, right? If we have a current here in the inductor, I of t, it gives rise to a voltage V of t across the inductor, correct? With me, guys?
Yes.
Now, I know the relationship between voltage and current in the inductor, and I'll put it right next to it, right here, that it's L times di of t dt is equal to the voltage across the inductor. With me? Now, please just follow me on this. I'm just going to do it one time. And then we'll use it. Now, if I take a look at this, if this is the current, then what's the voltage? Well, it's equal to I. Remember, this current is going to have the form, and I'll just call it I naught e to the j omega t. I made that point that if you're going to have a source voltage that varies as e to the j omega t, everything in the circuit is going to vary at that frequency. Have that component. Well, then I have to take the derivative of that. What would it be? Well, the derivative of this with respect to t would be the I naught comes out as a scale factor, but I'd have j omega, wouldn't I, first? And then I would have what? E to the j omega t times I naught. Just take a look at this and take a time derivative of the current, because that's what this formula says. If I want the voltage here, I simply say that it's equal to L times di dt. Derivative of this with respect to time just brings out a j omega. But I know that V of t here will have some value, V naught times e to the j omega t as well, correct? It's going to have the same temporal variation. Now, this is the essence. And I know whenever I talk about resistance in general, if we're talking about in the DC domain, resistance is just the voltage over the current, isn't it, for a single element class? How many remember that? All right. This is exactly what we use when we're in steady state or at a constant frequency of excitation. So when we have an inductor here, we say that the inductor in the AC domain has not a resistance, but an impedance. The symbol is Z. Now in the book, they'll use X, but just use Z. Z is a symbol for impedance. It means at a constant frequency, a constant AC frequency. And the impedance of that is going to be equal to V over I. Now take a look at this. If I look at V over I right here, this is the voltage, right? Isn't that the voltage across the inductor? So let me put it down here. Hopefully you can follow me. When I look at the impedance for the inductor, this is for in the inductor, I'm putting sub L, it's equal to V over I, and this is in the phasor domain. So it would be equal to this, that's the voltage, it would be equal to J omega L. I put the J omega first because it's most commonly done that way, times e to the J omega T times I naught. And then if I divide by the current, I define the current up here, right? If I define it by the current, I have I naught e to the J omega T. Now take a look at that just one time, but you all see that I've defined the current, right? And I've got the voltage from the mathematical equation, the definition, right? If you're a little uncomfortable with it, just go with me, you're going to see it. How many understand what I'm getting at? What don't you see, Susan? You gave me a look like I don't know what you're talking about. I get that a lot.
Electrical engineering isn't my strong suit. I'm trying.
That's all right. That's all right. Believe me, fine art isn't mine either, but my wife appreciates it. So I try to understand that too. Anyway, when I come here, the thing you should see is I naught goes away and the exponential e to the J omega naught T goes away. Do you all see that?
Yes.
Now here's the beauty. This is like an AC, write this down. It's like an AC resistance. All right, that's all it is. So if you take the impedance ZL, and this is if you're at a constant frequency of, and you got an inductor, you just replace this inductor with an impedance. And that impedance is simply J omega L. So write that down. I'm going to do this again. Now, if we have a capacitor, I'll do this now. If we have a capacitor as such, there is a current and a voltage
Can you move
across
the paper up?
Yeah. If we have a capacitor, if there's a current and voltage, the relationship is what? C times dV dt is equal to I. How many remember that from physics? C dV dt is equal to I for a capacitor, for an inductor is L di dt is equal to V. Well, if this is true for a capacitor, I'm going to assume the capacitor voltage V of t is equal to V naught e to the J omega t. Now, I'm doing this because I made the statement earlier that the voltages will all vary as e to the J omega t, and they'll be scaled by some value V naught, remember? All right, so I'm just explicitly stating that. Now, what's the current going to be? Well, the current's going to be what? C times dV dt, right? And dV dt means I take a time derivative of that. So really, I can do it this way. I get J omega, right? Time derivative of this brings out the J omega, right? Times C, because there's a C here. And then it's going to be times V naught e to the J omega t. Let me rewrite that. I of t is equal to J omega C times V naught e to the J omega t. There's the current. This was the assumed voltage. And when I get the ratio of voltage to current, that's called the impedance of the capacitor. This is the impedance of the inductor. This is the impedance of the capacitor. And that's simply going to be 1 over J omega C. Now, the units for the impedance are ohms, just like resistance. And ohms implies it's a ratio of voltage to current across that element. Okay? Now, I want you to bear with me. I'm trying to get to the essence of this, but y'all see what I'm doing here so far? So here's after all that discussion. The thing you take from this is an inductor has this AC resistance and a capacitor has this AC resistance. One other thing I should say about the capacitance resistance. Well, what is 1 over J, anybody?
J to the negative 1.
Minus J, right? Yeah, it's just equal to minus J over omega C. And something else I'm going to tell you is this. Let me just finish this with a thought. That when you have J, you can represent that as a polar number. That's really just equal to e to the j pi over 2. Now think about that. Isn't this angle 90 degrees? So if I have e to the j pi over 2, it's got a magnitude of 1, and it's at 90 degrees to the real axis, which would be just j, right? You think about that. When I take a look at the vector e to the j anything down here, what I really do is have that angle theta between the real and the imaginary axis, right? And if theta is 90 degrees, then it's just j, isn't it, class? How many see that? Got to make sure you see this, because what would this be? What would, if I put, don't use this, what is this equal to? E to the minus j pi over 2, anybody? It's got a magnitude of 1, but which way do I go in terms of the angle? This way, right? So wouldn't that be minus j? Y'all see that? One more question for the crowd. What is e to the j pi equal to? Class, look at the thing. What's pi in terms of degrees?
180.
It would be over here. What value would that be?
-1.
Right, -1. By the way, it doesn't matter if it's plus or minus j pi, because whether you go around clockwise or counterclockwise, if you go 180 from the real axis, you end up at -1, right? Okay, now, what you've been dying for is to see a circuits problem solved with this, all right? Here comes the whole 9 yards. It's all going to come together, so pay attention, and you're going to like it, I think. So I'm going to first set up a real problem that somebody's going to give you when you interview, possibly. Now, if you have not interviewed yet, you're in for a treat from some of the high-tech companies. They have established ways of figuring out just what you're worth in terms of your intelligence, as well as your understanding of the basic material. One of the things they do is probe you. And here's a typical probe, because if you're a guy that just had differential equations and you never really paid attention in circuits, then you're not going to know what to do with this one. So I'm going to put a voltage here. I'm going to say it's 10 cosine of 30t volts. And then I'm going to have a resistor here of 10 ohms. And I'm going to have an inductor here of 2 henries. So that's equal to L. And the guy, this is a voltage. This is V of t. The guy wants you to figure out what I of t is. So that's the question. Y'all follow me? Now, you could write a differential equation in terms of I. We know L times di dt is the voltage across this, and I times R is the voltage across that. We could set it equal to 10 cosine of 30t and solve the differential equation, probably using Laplace transforms. And you wouldn't be given any kind of a formula sheet. So they would assume you're familiar with enough with Laplace transforms so you could solve it. And then you would not like that. And that's okay. Because here's how a circuits guy does this. The minute he sees this, or you see this as an engineer, you realize that's at a constant frequency, right? And I'm just going to write omega here is equal to 30. Do you all agree with that? With me?
Mm-hmm.
Now, instead of doing a cosine, I'm going to go ahead and put in the phasor voltage. Now, this is important. I didn't cover it. For a phasor voltage, if you have V naught cosine of omega naught t plus a phase angle, in terms of the phasor voltage, this is when we go to the frequency domain, when we have those J, the reactive elements will have either we'll have J omega L or minus J over omega C. This becomes, you leave a V naught alone, and you just put this right here at an angle of phi. You suppress the e to the j omega t term because they will cancel. I'm trying to get this lecture in time. So the only thing you retain is the magnitude and the angle. You suppress the frequency. Do y'all follow me on this? Now, please follow me. I'm going to show you how it's done. With me on this one? And if you're a little, think too much is coming at you, just brace yourself. It'll be all right. So for this source becomes simply 10 volts at an angle of 0 degrees. Well, if it's at an angle of 0 degrees, I don't even need to write that. Do you all follow me? That's the voltage. Got me, class? Now, when you've got a resistance in the continuous time domain, when you go to, and I'm calling this sort of an umbrella thing, I'm calling it the phasor domain because of what we're doing. You leave it alone. That 10 is just 10 ohms, which is nice. Okay? You got me, everyone? Just hang on, you're going to be all right. Now the inductor, you draw the inductor in here, but you say the inductor has an impedance. It has an impedance of J omega L, right? Now, J is J, omega is 30, correct? You got that by looking at the coefficient of T, didn't you, class? How many see what I'm saying? You identified omega by looking at the coefficient of T inside the cosine argument. So it's times 30, and then it's times L, which is 2, or J 60 ohms. Do you all see that? Please take a careful look at this. Give me a show of hands if you understand what I've done here. Now this is just like AC resistance. Now if I want the current, this is a voltage, remember? And I think in the book you have, they put a little tilde over something that's a phasor. It means it's in the phasor domain. It's got real and imaginary parts. If I want this current I, which will be a phasor, I get it just as if these two were just resistors and this was just a voltage source. The way I get current, you all agree they're in series, right? Because they have the same current through them. Agreed, class? So the way you get that current is you take the voltage, 10 at an angle of 0 degrees. You don't even have to put the angle down if it's at 0 degrees. Divided by this, which is going to be 10 plus J 60. Now, I want to tell you, you're going to thank God for your calculators because your calculators can do this in a heartbeat, this mathematics. Technically, this is going to have a magnitude and an angle. Now, watch. Do you all agree that 10 would be up here, but downstairs, the magnitude of this would be the square root of 10 squared plus 60 squared, right? Square root. Do you agree with that? As far as the magnitude of this? And the way you do this, by the way, I didn't say this explicitly, the way you get my current or any other solution to these things is you do it in terms of a polar number almost always, and I'll show you why in a second.
Wait, can you move the paper down?
Yeah, can you see it now?
Yeah, and one question. So for the bottom, how did you get 10 plus J60?
All right, you see right here is 10 ohms, right?
Yeah.
All right, and you see this is J omega L, right?
Yep.
All right, so that's J times omega, which is 30, right? 30 times what? L, which is 2, so it'd be 60, wouldn't it?
Yes.
Okay. That's where I got it. They're two series resistances. One strict real, the other strict imaginary, and I added them together because they're in series, just as if I would if it was just 60 ohms. Agreed, class? Now, yeah. That's the magnitude, but the angle downstairs, and how do you get angle if you have a real and imaginary number? Well, it would be what? It would be the inverse tangent of 60 over 10, wouldn't it? For the angle downstairs.
We can't see what you're writing.
Huh? Oh, I'm sorry. The angle would be, if you think about this, 10 plus J60, if this is 10 and this is 60 here, and this is the J domain, then this angle right here is opposite, or 60 over adjacent, which is 10, and it's the inverse tan of that, right? Opposite over adjacent is tangent, therefore the inverse tan would be the angle of 6. Agreed, class?
Where's the 10 on top?
Couldn't understand you? Say that again.
I was just curious where the 10 on the top came from.
I couldn't understand what you said.
She's wondering where the 10 on the top came from.
It's not on the top. This is, that's the voltage, 10, right? You take the voltage and divide it by the resistance to get the current. It's just like a regular circuit. Here's the voltage 10. See it? It was what? It was 10 cosine of 30t. We got rid of all that and turned it into a phasor, which is this magnitude and angle, right? Now bear with me. Okay. Now y'all see this. It's inverse tangent of 6 over 10, or really, I'm sorry, 60 over 10 or 6. What happens when this comes upstairs? It would be 10. This would be still the magnitude square root of 10 squared plus 60 squared. If you got a calculator, if you don't mind doing this, I'd appreciate it. Now, if the angle comes upstairs, it becomes what? Negative, right? So it'd be negative 10 minus 1 of 6. You all agree with that?
Can you scroll down a little bit?
Yeah, thank you. Now I'm going to ask.
Is this angle still in radians?
Yep, here it is. Or you could ask for it in degrees or radians, couldn't you? When you do an inverse tan, you could get it in radians or degrees, right? Class? Depends what you calculate. I would suggest that, well, I would do this in radians for a bunch of reasons. You may like degrees, but so this would be the angle. Now your calculator should do this easily. Can anybody tell me what this is if you have a calculator? I have a calculator, but I got to shut down a few things to use it. Anybody?
Yes, sir, I got it.
What's the magnitude?
It said it was 1 over 37 minus 6 over 37i.
Magnitude has no I.
Then 1 over 37.
For this?
That's,
No,
I'm in
no.
degrees. My mistake. Let me switch
No,
over.
this is, you're thinking of this calculation. I just want the magnitude. It'd be 10 over 10 squared plus 6 squared. Really, what is that? I can factor out the 10 here. So that would be really what? 1 over square root of 36. It's 1 over the square root of 37 would be the magnitude, right? You can do this, 1 over square root of 37, which is about what? 1 over 6 almost, right? And the angle would be minus the tangent of 6. And now you can give that to me. What's 1 over the square root of 37? About 1/6, isn't it? I mean, think about it. Square root of 36 is 1 over 6, right? I know you guys know this.
Wait, so why is it minus tangent?
Well, think about it. When you're downstairs, if I had like 5, right, and I divided it by 2 at an angle of 30 degrees, right? Isn't that really 2.5 at an angle of minus 30 degrees? Because whenever you take an angle from downstairs to upstairs, you get a minus sign there, right? Do y'all remember this class? When you had your calculus courses. All right, so that's what happens. The angle, if it's downstairs, becomes, you flip the sign if it goes upstairs. I'm going to remember that, and I'm trying desperately to get this in time. Now, what is the angle for this one? What is 1 over the square root of 37? I'm going to flip the page. Anyone?
You want inverse tangent of 6 or tangent of 6? Negative tangent of 6.
Tell you what, I'll do this real quick on Octave, if I can. When I'm in person, kids have calculators and they whip through this stuff. Octave comes up, that is. There we go. So in Octave, I'd have a magnitude equal to 1 over SQRT of 37, 7, right? So that's the magnitude, and then the angle would be minus a tan of 6, and this is going to be in radians. And then if I want that in degrees, it's times 180 divided by pi. So it's minus 80 degrees, roughly 80.5 degrees. So I'm going to use that and say that what that means is Put it right there. But now I have the actual resulting solution. I have I phasor. Let me finish this thought, and I know I'm out of time. I phasor is equal to 0.1644 amps magnitude, and it's at an angle of minus 80.538 degrees. Y'all follow me? This is a magnitude, that's an angle. Do y'all follow me, class? I left it in degrees for a reason. If I want to go back to the time domain, I of t would be equal to the real part of I phasor times e to the j omega t. Now I reintroduce the e to the j omega t. This is the magnitude. This is the angle. And here's exactly what happens. Because I have e to the j omega t here, I know I'm going to have a cosine of omega t plus j sine omega t. I'm just going to conclude with the answer. I of t here, and you're going to like this, is going to have this magnitude, 0.1644. Then it's going to have the cosine, as it was before. Remember how we had omega equal to 30? The 30t goes in here. And then you add the phase angle. Now you'll notice this is minus 80.538 degrees, right? I want you to pay attention to this. It's very important. I left that in degrees because you're familiar with it. That's just about minus 90, isn't it? Right? Now here's the thing that's important. What is omega in terms of? That's radians per second, isn't it? Right? Radians per second times seconds, time would be seconds, would be radians. So this really needs to be in radians. And you're going to find a lot of stuff in the internet where they don't do the change. Do y'all follow me on that, class? This should be in radians if you wanted a true time domain solution. So instead of the 80, I would have minus 1.4056 radians. And that is radians, and that would be the time domain form of the current. Do y'all follow me? Now let me recap what I did, and this is an office hour. I'm 2 minutes over, and I'll probably get some hate mail from people that have to go because they have to go, and I'm appreciating this, but this is the office hour, and I just want to recap. Here was the original problem that I gave you. I gave you a voltage source, a real resistance, and an inductance, right? What I did was this. I said, I'm not going to work in the time domain. I'm going to work in the quote phasor domain. I use this information here and go into the phasor domain. I take the magnitude of that voltage and I replace it down here. This was in the videos if you watched them. Did anybody here watch the videos I gave? The links? If you watched them, John, you probably see some of this stuff. You're recalling what she covers and what I'm covering. That's the reason I did. Well, I just take the magnitude and the phase angle. The phase angle is 0. Now that's my phasor voltage. The 10 ohms becomes just 10 ohms. Resistors translate seamlessly. Then I take that inductor, 2 henries, and I replace it with its AC resistance, which is j omega L, right, class? Everybody with me? Now I solve for the current I, as if it was just a regular DC problem. I take the voltage of 10 at an angle of 0 degrees, so I don't need the degrees, and I divide it by the series, not resistance, but impedance. I take 10 plus J60. Now this, believe it or not, is the right answer in the phasor domain for the current, but it doesn't allow you to go to the time domain because I asked for the time, your boss, the guy that's, your interviewer would ask you for the time domain form. Do you follow me on that, class? And at the time, you're going to be surprised how many people will actually probably do this problem with a Laplace transform at an interview. And it's crazy. It's so simple don't use Laplace transforms if you got steady state voltages. Constant frequency voltages. So we translate this from a rectangular number to a polar number, magnitude and angle. And then from there, the only thing I do to get it into the actual time domain, hang on. Hello?
Hi, Mr. Baginski.
Hey.
The surgical clinic.
Yeah, I'm in a class right now. Can I call you right back? I'm teaching on Zoom.
I'm actually leaving, but Dr. Thomas said to keep taking your medicine.
All right, thank you very much. Sorry, are you? Long story. It's from the surgical clinic. Anyway, y'all follow me what I did to get back to here? And the key thing is just the magnitude that I got from the phasor thing and then putting in the angle there. Same cosine of omega t form. Agreed?
This is possible because the voltage doesn't have a phi.
Well, the voltage, if I added a phi, then it would show up right here.
Okay, you said constant frequency voltage. How do we tell that's constant frequency?
Let me rephrase what I said. This is at a constant frequency 30, right? See, it's cosine of omega t plus a phase angle. Phase angle has nothing to do with the frequency. The frequency is the coefficient of t inside a cosine or sine argument. Whoever asked that. Are you good with that?
Yeah, thank you.
Sure. And the frequency is 30. That's 30 all the time. There's no time. It never changes. Now, the phase angle, if I put a phi in here, then there would be a phi here, wouldn't there? And this is sloppy, but you all follow me? And if there's a phi there, there would be a phi here, right?
Yeah.
And then if there was a phi there, there would also be what? Plus a phi there, right? In other words, this right here would be added. If this was a phi of, say, 20 degrees, it'd be 20 degrees there, 20 degrees here. And then you would have to add, or maybe not 20, say pi over 6 or whatever. You would have to add the two angles together. In this case, you would subtract 1. Okay?
Okay, thank you.
All right, guys. All right. So now this is the office hour, and I was going to say that I'm going to assign some problems for Monday. And some of you, and I know somebody has a question about the quiz, no doubt. What chapter is this in? Well, it's in about 3. But Jamie, I'll tell you that in the book, he goes right after chapter 2 and 3. He's mentioning this, and he mentions complex math even in the first chapter in his book. Unfortunately, he doesn't go into detail. Now, I spend time doing this because I know that a lot of people don't recall this. I've taught this class, and I know people are clumsy with this stuff, okay? Now, I'd like to do another problem, if you don't mind. Good with it? Remember, all the things that you learned before apply to these, to what we're doing here. And something else, even though I didn't have a time, just because we didn't get through enough of this, I'm going to postpone the quiz until Wednesday. We may have one Wednesday and then one Friday, but for sure, it can't do it Monday simply because I didn't get enough of this material out to feel comfortable with it. I want to do one with a capacitor, okay? With me? All right. And I can pick one out of books. I can use your book if you want, or the book for this course. Doesn't matter, but let me do this. This is actually quite a pretty good one. Suppose I have an inductor there, resistor here, and then I have a current source here, and I have 2 amps cosine of, say, 30t. This is going to be amps. I'm going to make this 1 ohm, make this 2 ohms. And I'm going to make L here 1/2 of a Henry. Y'all follow me? That's the, oh, I was going to put a capacitor. I put an inductor in there. We'll do one with a capacitor in a second. Y'all follow me? What I've got here?
Yes.
And here's what I want. I want the voltage across these 2 points. All right. And I want this in the time domain. Do y'all follow me on this? Now, again, this is in the time domain, right? So right away, I go to the frequency or phasor domain, and I replace this inductor with its AC impedance. So what is the AC impedance going to be? It's J omega L, right? What is L? Anybody? Class? I mean, sorry, what is omega? Pardon me.
Oh, 30.
And what is L?
1/2. Is it
And L times omega would be
15?
15. So this is J 15 ohms, right? Agree? Now take a look at this. That's J 15 ohms. Now I've got 1 ohm here. Then I've got 2 ohms here. What about my current? What's that going to be? It was 2 cosine of 30t. What does it become in the phasor domain, class?
2 and then 0?
At an angle of 0, or just 2 amps, right? You don't need the angle of 0, do you?
No.
Here you suppress the omega. You don't need it. Now, I wanted this voltage, right? Let me go through this. I've got a current flowing. Do you all agree that current flows through each element? Yeah, right? They're in series. So what's the voltage here? It would be 1 times 2 or 2 volts, right? Agreed, class? Y'all see what I'm talking about? If I got 2 amps into 1 ohm, I got 2 volts, don't I?
Mhm.
And then what's the voltage here? Well, it would be 2 times J15, right? Or it would be J30, right? Volts. Agreed? People? Yay?
Sorry, where did you get the 2 voltage?
Say that one more time.
Where did you get the 2 voltage that is?
Right here?
Yes, sir.
All right. The current is 2 amps, right?
Mhm.
The resistance is 1 ohm.
Oh, okay.
2 times 1 is 2, right?
Yeah.
Now, we want this voltage, right? Take a look. How do I get that voltage? I know I'm using this, but I'm trying to not clutter things too much with a single color. I start at the negative terminal, right? What about this? This is a
Increase.
of J30, right? You're not used to seeing a J there, but it's J30, correct? And this is a
Increase of 2 voltage.
right, and that's V out, isn't it, class? Now, can somebody tell me what the magnitude of this is in the angle? You have your calculators, don't you?
Yeah.
So what's the magnitude? It's about 30. You'd have to take 30 and square it, right? That's 900, right?
It's 30.06.
Yeah, and what's the angle? You can give it to me in degrees. So it's what? It's the inverse tan of 30 over 2 or inverse tan of 15. You can give it to me in degrees. It's just about 90. I can do that too over here if you don't want to do it.
I got it. It's 1.50. Oh, wait. Oh.
That's radians. That's okay. So in radians, it's 1.5042. And
86.19 for degrees.
I think you are right. Yeah. 86.19 degrees. And remember that will have to be in radians when we go to the time domain to be correct, right? But degrees is something you got an appreciation for. It's about 1.5042 radians. Now that's in the phasor domain. To go to the time domain, we would say V out of t has this magnitude, 30.06, right? And then it's going to have cosine of the frequency, which was 30, right? So it's going to be times 30 t and plus the phase angle. Don't put it in degrees if in the time domain, because that's radians. So in radians, it's 1.5, I'm sorry, 1.5042, is that right?
Mm-hmm.
And that's radians. And that would be the value of the voltage there. Y'all follow me? Now, in some of the problems, and I'm just going to show you the class this, because these problems, I think I'm going to use some of these problems. I'll use some out of your books too, probably some from other sources. I just want to show you this and go through it. This is the problem I actually was using, but I didn't put a J2 there. Here, they replace the inductors. The only thing they want is V out, but they just want in phasor form, magnitude and angle here. Now you see that that J2 is already assuming that you got the omega times L, the product, and they just put it in there. You all with me on that, class? Let me ask you this. Suppose we looked at this problem right here, 418. All right, I could put in a time varying source here, make it 6 cosine of like 30t plus 0 degrees. But if we're fair and honest to each other, in the phasor domain, it'd just be 6 at an angle of 0. Do you agree with that? And the only thing we'd use the omega for in the phasor domain is to get the capacitive reactance, right? Can you all follow me on this one? Capacitive impedance. So capacitive impedance for this one is simply 1 over j omega c or minus j over omega c. So what it's really saying is 1 over omega c is 2 here, right? Follow me? And the minus j is retained. Can you see what I'm talking about? That it's got a minus 2j. A capacitor has an impedance of minus j over omega c, right? The product of 1 over omega c is 2. Now we don't have to fuss with the time domain form here. If I just want the phasor voltage here, how would you get it? Anyone? Think about that. Anyone?
You would get the voltage at the 1 ohm resistor and then the voltage at the capacitor, and then you would go around like we just did.
Yeah, but that's implying you know the current, isn't it?
Oh, yeah.
How about something, and I want everybody to listen. Doesn't this look like a voltage division circuit? Don't these two look like they're in series? And doesn't this look like it's in series? So doesn't it look like I take 6 volts and I want the voltage across a portion of the series resistance? So this V naught, and I'm going to do it over, can you all see the problem, class?
Yes.
That voltage V naught would start with the 6 volts. You would put 6 at 0 degrees, and then you would multiply it by 1 minus J2 on top, and then you would divide by the sum, and then it would be divided by 2 minus J2 on the bottom. Are you with me? Think about that. This is a series circuit, isn't it? Can everybody see this?
Yes.
All right, so if I did a redraw on this circuit, I'm going to have to move this to do the redraw over here. If I did a redraw, just drew it again and try to just stretch those wires and make it a little easier for you to see, then I would have 6 volts at 0 degrees here, and I would have 1 ohm here, and then I would have the 1 ohm here and the minus J2 here, ohms here, and I would connect this circuit and I would want this voltage now. And I can see if that's 6 at an angle of 0 degrees volts, this voltage V out would be equal to that 6 at an angle of 0 degrees times this impedance, 1 minus J2 over the sum of this plus this, or 2 minus J2. Y'all see that, class? Now, you need to get this in terms of a real and imaginary part generally. That's the way I ask for answers, polar. I'm sorry, not real and imaginary, in terms of a magnitude and an angle. Now, y'all have calculators, right? Your calculators, the 84s, the 89s, the Inspire, the 93s, and whatever other version of TI you have, or any other, I mean, for your, if you're an HP person, it does, I don't even know the model numbers anymore. Or if you're a Casio, I don't know the model numbers on them. All these, you can just look up online, type in complex number calculations or matrix solutions, complex number linear algebra solutions in the name of the calculator. There's tons of stuff on the internet that'll help you. I'm using Octave because it's available to me and I can get the answers right there. I can show you. All right, now if I want this one, does anybody here have your calculator with you before you? Anybody at all?
Yeah.
Yes, sir.
If you do, which kind of calculator do you have, John?
I've got a TI-84.
How about you, Kellen? Do you have?
Yeah, I have a Casio 115 ES.
Not familiar with Casios. Jessica, what about you?
I have a Texas TI-83 Plus.
All these, well, I don't know about the Casio, but the TI 83, 84, 89s, all those do these things seamlessly. And if you want to check your answers, Octave's free and you can download it, or you can just link into MATLAB. But y'all see this right here, right? All right, now if I put this, if I want to solve that, so I'm going to just try to do this. So I'm going to call it V0, and this is Octave. It'll be the same in MATLAB. It's just 6, forget the angle. All right, and on top I have 1 minus, and then to get the J, you have to have 1J. It's actually times 2, right? You got to put a 1J, just not J, times 2. And then divided by, and then it's going to be 2 minus, actually, you could probably put the 2 in front of the J and that would work too. So when I get this, you see how I get this for the answer? Y'all follow me? Now that's a real and imaginary part, but I want it in terms of a magnitude and an angle, right? So your calculators will just have 2 functions. You'll hit a function and then it'll go like rectangular to polar. And I don't know the keypad on your 84 and 83, but it's going to be something like that. It's a 2-stroke thing. And if I want the magnitude, it's ABS here of V0. That's the magnitude. And then the angle of this is argument, I believe, on, oh wait, no, it's either angle or phase, I forgot actually. Angle of, let's see if that's it. Yeah, and if I take that times 180 divided by pi, it would be in degrees. So it's at minus 18.45 degrees. And I would use Octave or MATLAB or MathCAD to check until you're convinced your calculators are spitting out the right answers. I use MathCAD all the time, by the way, because it's much, much easier to do these things. Okay. Are you guys okay with this so far? How many feel at least they've got enough confidence to give it a shot and compare answers? You okay with that? 1, 2, 3. I'm hoping you do. And I know this is my office. I'm going to tell you one other thing about this. If you spend time right now doing them over the weekend, even though I'll announce it to everybody, I can't get a quiz in because we don't have enough time spent on this. We'll do it on Wednesday. You will be surprised at how much it pays off in your understanding, because we're going to move into some theories and other things, but it's real important for you to get a feel for solving phasor equations like this. In other words, having complex resistances, impedances, okay? Do you have, when is the next quiz? Did anybody hear what I said, class?
Mm-hmm. We have Wednesday and maybe on Friday.
You're probably going to get 2 in a row, but I've got to talk to my grader and stuff. Did anybody go get their quizzes from the grader?
I emailed him about getting them electronically.
You can't for the second one because it was on paper. You mean the first quiz? The first quiz, they're trying to upload the thing. Is that uploaded yet or not?
I'm not sure.
Well, I apologize. I don't know what the problem is with the software, but you're supposed to upload these things in a zip format. And we have done, as far as I know, everything exactly right. But for some reason, there's a problem. So okay. All right. I'm looking at some of this stuff. Do you have any other questions? Because I'm going to give you some problems with the answers and or solutions and answers, and I'll let you go at it. But the nice thing about what I'm doing is, if you look at his book, now if you read through this, he is very terse with explanations of stuff. And he doesn't spend much time on like phasors and things like that. He just blows through it. But here's his problem. Here's a typical problem he's going to give. It's on page 57. He says if you have this 8, that's the capacitor, there's an inductor. Here's the voltage supply. He wants you to solve for the current. Can you all see that?
Mm-hmm.
Now, from what I just told you, you know you're going to turn this into a phasor. And unfortunately, what he's doing in his book that I'm not going to do, he put this in terms of a peak value and put this in terms of RMS. This is peak and this is RMS, and it'll confuse you, don't worry. And now, have you heard the term root mean squared in your courses yet? Or effective, don't worry about it. This should be the peak value down here. It should be 141.4 at an angle of 0 degrees, but don't worry about that. Then he replaces this with 8 is 8, and he just finds the frequency here is 377. He multiplies that by 0.663 right here, and he notices it's millifarads, so it's times 10 to the minus third, and he finds out, takes that, and then he takes 1 over that and puts a minus j and gets the capacitive impedance. For the inductor, he has 26.53 times 10 to the minus third times 377 times j, it gives you 10. And now he has 8 minus j4 and plus 10, and he wants the current. Follow me? Now just listen, this current is as easy as it looks like. That current is going to be this voltage divided by the sum of these impedances. So it'd be 8 minus j4 plus 10, j10, or it's really divided by 8 minus j6. Do y'all see that? And again, I want to say something. He's making this more complicated than I would. This is called the root mean squared value. It's this value divided by the square root of 2. I don't want to mess with that. For now, don't worry about his examples here, but that's what he's doing. And in his book, oh boy, he covers a ton of stuff in one chapter that I would not normally cover this quickly. And I didn't do this, but I'm just going to, your common sense will get you through this part very easily. Remember I said that these are like AC resistances, right? Now take a look at this. These two in series would have a value of 9 plus J16, right? That has a magnitude and angle, right?
Yes.
It's all right. And he wants an equivalent parallel combination. Now here's the thing. You would have to assign this value R and assign this value J, and just, you can call it X here. And then you would have to equate these two things. So you had 9 plus J16 is equal to, well, if they're in parallel, what do you get? You get 1 over R plus 1 over 1 over jx, and you would equate them and solve for the real and imaginary parts. He's saying if for this to be equal to this, that's how you do it. I'm not going to give you this stuff, class. I'm going to give you my own. They're not going to be, or they'll be either out of Irwin's book or some of the other books, because this stuff that he's doing here is making it a little harder than it needs to be. That's the reason I'm giving you my own problems. I mean, I'm giving you Irwin's problems and stuff out of, I've got, whatchamacallit, Hayton Kimmerly, and I got a few other books here that I'll be dealing with. How many of you remember doing imaginary math before? You guys remember it? You've had to do that in your mathematics courses, but frankly, I don't remember everything that was involved with what you got. Okay. We can, I guess, cut away for now, and I'm going to give you some homework. I expect you to do it. I'll probably give you, I don't know, I'm going to say 2 to 3 hours worth. But if you've paid attention today and you've got octave, or you know how to use your calculators, you should blow through this thing probably inside of 40 minutes, maybe even 30 if you're good. In other words, the problems themselves are not going to require a huge amount of trickery or anything like that. They're just going to be something where you're going to just use capacitive inductive reactances and find out what in fact the current and voltages are in the phasor domain and then in the time domain, okay?
Dr. Baginski, can you please do one with the capacitance?
Yeah, sure. Why don't we do this one? Since you asked. This one I'm just going to create, all right? So I'm going to ask you this. If I have a voltage, 20 cosine of 10t plus pi over 2 radians. Now that's radians, okay? Volts right here. And then I have a resistance of 20 ohms. All right. And I have a capacitance equal to 0.05 farads. And I want 2 things. I want the current I of t, and I want the voltage V of t across the capacitor. Can you see this, everyone? Okay.
Yes.
All right. Now, what do I do with this? And for the record, I don't know why this camera keeps going out of focus. With me? All right, what do I do with this? Well, first thing, how about we write down what omega is? It's 10, right?
Mm-hmm.
It's assumed radians per second. So I got omega. The phase angle is pi over 2, right? So that means I got a source here, a source voltage, plus or minus. And it would be what? It would be 20 volts at an angle. And if you want to put 90 degrees, you can, because pi over 2 is 90 degrees, isn't it?
Mm-hmm.
Right? Or you can put pi over 2 radians. So you could put 90 degrees. I'll come back to that. Now I replace the resistor with its value is 20 ohms, right? All right, now what about this? Well, capacitive reactance was what? Or impedance. It was minus j over omega c, correct? Guys?
Yes.
All right, so omega is 10, so this would be minus j over omega 10 times what? That's 1, 2. So it's really 5 times 10 to the minus 2, correct?
Mhm.
What's that going to be? Well, 10 times 10 to the minus 2 is 10 to the minus 1, right? And 5, 1/5 is really what? 0.2, isn't it, class? I mean, this is really going to be what? It's minus j, and then if I have 1 over 5 times 10 to the minus 1, right? That's really 1 over 0.5, right? Or 1 over half would be 2. So this should be minus 2, correct, class? Minus j 2 ohms. You all see what I'm doing here? Jessica, do you see that?
Yes, sir.
And James, do you see?
Look,
Do you see what I'm doing here? Minus j 2 ohms.
I do.
Okay. I want to make sure. All right. Well, how do I get this current? I'm going to show you a trick right here. 20 at an angle of 90 degrees is simply J20. Because 90 degrees is just J, right? If you think about it. So what's this current going to be? What is my I phasor going to be? It would be the voltage, right? And I could put that or that. I'll put the J20 divided by what? You asked for the capacitor, Jessica. What's it going to be?
It's 20 minus J2.
Right, 20 minus J2, right? Now I'm going to pull in my, and you've got this too, your calculators. This is my calculator today. So I'm going to go ahead and find the magnitude of my current I. And that's just going to be, well, I'm just going to define it. It's going to be 1J times 20 divided by 20 minus 1J times 2. And I get this. Now remember that I'm getting is got a real and imaginary part, right? And if you do it with your calculator, go ahead. And now I need to get the magnitude and the phase angle. So the absolute value of I is that. And the phase angle of I in radians, I'll get it in degrees. So it's times 180 divided by pi is 95.711 degrees. Let's see what it is, and in radians, it's 1.675 radians. So that means I here is 0.9950. And the angle is 95.711 degrees, or in radians, it's 1.6. I'm going to put degrees. Agreed? Are you with me, everyone?
Yes. Sorry, can you repeat again how you go from minus J 1, 5 to -2 to minus J 2 ohms?
Sorry, what? To go from where to where?
How you got the minus J 2 ohms?
All right. If I take minus J over 10, which is the capacitance, it's the frequency, right? And the capacitance is 5 times 10 to the minus 2, right? So what would that be? Well, 10 times 10 to the minus 2 is 10 to the minus 1, right?
Mm-hmm.
And if I have 5 times 10 to the minus 1 is really 0.5, right?
Mm-hmm.
Isn't 1 over 0.52?
Yes, I got it.
All right, that's it.
Thank you.
Now, this that I've got here is a magnitude and an angle, right? What would it be in the time domain? Class? Anybody? Come on, thing. Sharpen up.
Mm-hmm.
Well, wouldn't it just be the magnitude?
Mm-hmm. Yep.
And there would be cosine. Omega was 10t, right? And then what would we do? We wouldn't put 95.71 degrees. We would, if we were actually doing a calculation, we'd put that in radians, right? Wouldn't we?
Yes.
And that's 1.6705 radians. But that's how it's done. And that would be in real time. Now, since I'm going to ask you this, what about the voltage here? If I wanted the voltage across that capacitor right here, how would I get it? Here's a trick. Always work in the phasor domain. Do we know the current flowing here? Don't we know the current is this right here? Right? Y'all with me?
Yes.
Can you explain how you got 95.711 degrees?
Mm-hmm. You know, when I did this, let me just pull up my thing. John, follow me right here. When I was doing that, I said that I was J20 over 20 minus J2, right? The J20 was the voltage source, wasn't it?
Right. Yes.
And this 20 minus J2 was the impedance, the series impedance, right?
Right.
And when I do this, I get this number. Do you see that?
Yes.
Now, if you plot that, you notice the real part is negative, but the imaginary part is positive. That means it's greater than 90 degrees.
Mm-hmm.
And so I just get the absolute value of I, that's the magnitude, and then I get the angle. Well, I took angle times 1/8 over pi to put it in degrees. So it's 95 degrees, not 90, but 95. It's more than 90. We're into the second quadrant, right?
Yeah. And so what does the angle do to the I again in your function?
It tells you what the phase change would be. Let me go back here. When you do this right, when I'm right here, what I have to do for I of t in general, it's going to be a magnitude of I naught that I calculated. Then it's going to be cosine of omega t. That omega is the omega we started with, and it'll always be that omega, plus the phase angle associated with the phasor I right here. And the phase angle was 95.711 degrees or 1.67 something radians. That phase angle has to be included in the cosine form of the variation.
Okay, I was just trying to figure out like how I would do that on my calculator for a quiz.
The only thing you would want is magnitude and angle, right? You with me? Yeah. So magnitude goes here, phase angle goes here, the omega you just carry on from part 1. Okay? With me?
Yeah, I think so.
Okay. Callan, do you have a question? You're looking hard.
Yeah, so on the previous problem, we had our real part plus imaginary part for V naught, and to find the angle, we did the inverse tangent of the coefficient of the imaginary over the real.
That's the angle. Yeah, but your calculators will do that automatically, just like my thing did. Look.
Yeah, but when I put inverse tangent of 0.99 over 0.099, I get 84.2 in my calculator, not 95.
Which calculation are you talking about? Right here?
To find the angle, yeah. I found the magnitude all right, but then for the angle, I was getting 84.2.
For this?
Yes.
All right. Now take a look at that. If I want the angle of that, right? It's the inverse tangent of the opposite 0.999 divided by the adjacent, which is minus 0.09, right?
Okay.
Plot it. Plot where that is. Here, I'll just show you. I'm trying to, I'll have to pull off. When I take a look at this, if I have a real part of minus 0.099, it's really like what, minus 0.1 about. So if this is the real axis here, and this is the imaginary axis here, right? When I take a look at the real portion, that's point, it's about minus 0.1, it's about here, right? And the imaginary part is,
down, please.
yeah, and the imaginary part, sorry about that. The imaginary part is 0.99, about 1. So here it's going to be 1, right? Well, you see that this point right here would be greater than 90 degrees, right? Here's the real axis, which would be just 0 degrees, and then it's moving the hands of the clock from here all the way to here. This is the angle, right? Now you're calculating, I don't know what you're doing, but if you just put that value in, minus 0.09901 plus J 0.990099I, and then go, there should be you got an 83 or an 84 as I recall. If you just do the functional keys to take it from rectangular to polar, it'll give you a magnitude and give you an angle, and the angle will be 95 degrees. Now you're muted, so I can't hear you, Callan.
I said okay.
Y'all with me, everyone? Okay. I'm sorry we didn't cover more material today, but I felt I owed it to you to try to give you an explanation that made somewhat of sense. And since most of you, I don't think, looked, how many looked at the video here? Anybody? One,
I did.
two? Okay, that's pretty good. I figured I'd get about maybe 30, 40%, but those videos are great by that woman. Did you understand the lecture today?
Yes.
All right. Now, I don't have any news from Auburn University about COVID or anything. And does anybody here have any? Because I'm going to have to sign off here. I got some other stuff I have to attend to. Anybody?
I do have some news about COVID. From what I was told by the COVID Resource Center, pretty much any absences doesn't need an excuse for college engineering unless it's something major like class project, test, something along those lines.
Yeah, I don't know anything about that, but I can tell you that right now somebody asked a question about tutoring.
Actually, I did have that question. Apparently there's only one tutor for this class, and she's available like once every 2 weeks or so.
I frankly don't know anything about tutoring for this course. I've never dealt with tutors in my life.
Well, I didn't know if you could recommend anyone who would make a good tutor, or if we could get enough students interested, could we get meet up with a TA, one of the TAs sometime to go over homework and concepts?
Well, the TA is, Chun Li, and he's really good about helping people. Have you picked up your test yet, or your quiz, I mean?
Not yet.
If you have specific questions, I mean, if you want to get a group together, I'm sure he'd be happy to help you. And I'll answer questions after every class, basically.
All right, I appreciate it.
But tutoring is, I've never had to deal with tutoring in any of my courses per se. I know there are engineering tutors for things like calculus and stuff like this, but for courses, I'm not real familiar with, upper level courses. But I mean, if you got specific questions, that's what I'm here for during my office hour.
I appreciate the clarification.
Sure, but I'm right now, I'm very curious if there's any information about things happening around Auburn, closures, COVID-19 related problems, who to stay away from. And the reason I'm saying this is sometimes information is not publicly known through the newspapers or anything, but students know about it. But hey, if you don't know, then maybe it's good news. I know this much. I've got more or less and emphatically been told that barring like some kind of a disaster in the hospitals, they're not going to send everybody home. Now, I'm not saying they won't, but it's going to take more than 600 cases in a week to send people home, is what I'm saying. They're adamant about that they're not going to do it. And in this course, we are going to have quizzes in Brown Koppel, like the past one on Friday. And that quiz went pretty well, by the way. Did you guys have any problems with that?
No, the first question, I always sometimes like I see a problem and I always think of the big way to do it. I was doing a lot of things, and once you explain it, it was so simple to just get the voltage. But I was using Thevenin's. I started with nodal analysis. I was trying to get everything from the whole circuit. But yeah, the second one I feel was really easy. The one that had the mesh analysis, both were easy.
Yeah, I didn't actually look at, I mean, the problem is we got a whole bunch of zeros. So when we talk about an average of 6.5 or something, whatever it was, then what I'm doing is including a whole bunch of either people that didn't have a clue what they're doing or didn't even show up to take it. And that's a false, I mean, that skews data in the wrong direction. I don't know what else I can tell you. I get some homework out. I mean, the way I'm delivering the homework and the solutions, I hope it's helping. And here's one thing the last thing I've got for you two, because you're on here. When I look back on this course and my other courses, because I don't collect homework, and I leave it to you to spend time. I try to provide solutions because when I took courses, what I did is I worked as many problems as I could. And I try to compare my answers to the answers in the book. And if they weren't the same, that I went and reworked and try to figure out, always find where the mistake was. Now, I had solutions manuals for a couple. And they are useful if you can't figure out how to get the answer, to find out where your mistake was. But I always spent time doing a ton of problems and using the answers just to confirm mine. When students are left to themselves, what you'll see is the good students who are disciplined do very well in this course. The good students who are lazy or who have other interests, they do maybe a C. A lot of kids that expect A's get C's and D's in here. And the poor students who don't study flunk. I mean, they flunk like crazy in my courses. And I can't tell you the percentage, but and that's a really scary fact about especially things like the final exam, because it's comprehensive. So even though this isn't in your major, I hope people are at least getting a holy fear of a possible tragic outcome. All this stuff builds everything. And if you do what I tell you, spend 2 or 3 hours between every lecture doing this, regardless of what your friends are doing or your class projects, you'll be amazed at how easy it gets at the end. And if you don't, the end of this course is absolutely murder. Now you can see that AC resistance stuff. That's the only little twist you've got now, right?
Yes, sir.
Every other thing is the exact same. So now you're getting currents that are complex, but you can easily deal with them with your calculators, and it won't be hard. However, if you have uncertainty about Thevenin, nodal, mesh, combinations of resistors, things like that, then when we get into the next phase, we get 3-phase power and stuff, you're going to be so lost you don't even know what to ask. Trust me on this one. I've taught this and I've seen it. And I hate the fact that, you know, you had thermo, right? Or sorry, you had a course that had thermo, you had statics and dynamics all rolled into one, right? Or not?
Not for INSY, I don't believe so. No.
You had real thermo?
No.
You didn't have thermal.
Not for INSY, no sir, it's not part of our curriculum.
Do you have strength of materials or statics?
You can take it as an engineering elective. I took statics, but not dynamics.
I took fundamentals of engineering mechanics as my elective.
All right. Those courses, I was an electrical engineer, and I had to take the regular ME statics, dynamics, and strength of materials. I'm actually not sure if I took one I didn't have to take. And they're all 3 credit. And you know, those courses are, if you're a good engineer, in other words, if you're a serious engineer, you know your math, they're the same, they're almost the exact same concepts and everything as you get in circuits and stuff. I know they have moments of inertia. The sum of the moments of inertia is equal to mass times the acceleration. I mean, sum of the moments is equal to mass times the, it's the actual moment of inertia times the angular acceleration. But those kind of equations have parallels to electrical circuits and stuff like that. So a lot of this stuff, if you understand one, you understand the other. The thing that was always troubling, not troubling, that gave me that took more time to appreciate, was a lot of the physics that is not something you get a physical feel for, like quantum mechanics and solving Schrodinger's equations and different coordinate systems. That takes some getting used to when the boundary conditions aren't hard, they're soft. So that was the only thing I can tell you. But other than that undergraduate stuff, in terms of engineering and physics, it's really just applying mathematics. The same mathematics over and over again. All right. I'm going to have to go, guys. Do you have any last parting words? I hope this helped.
So,
No, sir.
you said the recording should save automatically, or I have to save it somehow? Like to my
It should ask you if you want to save it on YouTube or if you want to save it on Zoom or whatever they call it, the cloud. I would save it on YouTube.
On YouTube. Okay, sir.
Just give it a shot. Okay.
All right. Thank you.
All right, man. Take care, everybody. Okay.
Have a good day, Dr. Baginski.
You too.